Hello everyone, welcome back to my channel and it's me Akhil KK. In the last episode we covered the waypoint follower, or simply the basic objective of a self-driving car. And in this episode we are going to address one of the real world problems, and then we are going to build a solution or a software or a system in order to avoid that in our vehicle. And the problem is nothing but frontal collision. So our vehicle should avoid any collision when it is navigating from the starting point to the destination point. And yeah, let's have a look into our problem. Yeah.
Till now, there were no vehicle or pedestrian was present in the scene, and the road was completely empty. Now let's see what happens if there is an obstacle on the ego vehicle path. For that, we will launch another vehicle and bring it into the ego vehicle's path and see its behavior. So for that, let's prepare phase 1 demo. Now I'm going to launch the second vehicle in the scene. You can see the second vehicle already launched, and it's available in the map with red color, and the green one is our ego vehicle. And here is the second vehicle launched, and this is the ego vehicle. Now let's choose a goal pose so that the ego vehicle will start following the road, and we will manually drive and keep the second vehicle in the route to create an obstruction for ego vehicle. And let's see how ego vehicle reacts to such a situation. The ego vehicle is approaching. Now you can see the ego vehicle simply crashing to second vehicle. So basically this ego vehicle is not having any system to handle such a situation. So the only mission of ego vehicle is to follow the route. So that's what you can see here. To handle this, we need an obstacle avoidance system. So what is really needed to build one? A couple of sensors for object detection and depth estimation, a software section to monitor and predict possible collisions, a control section to control the ego vehicle to avoid possible collision, and the required sensors: a front-facing RGB camera, a depth sensor for depth estimation, a semantic sensor for object detection and localization. And then how to attach custom sensors to ego vehicle. Create a custom object description file for the ego vehicle, add the required sensors in the description file, and spawn the ego vehicle with the custom object description file. Now let's prepare custom vehicle description file. For that, first start CARLA server from a new terminal. Then open another terminal to launch the ego vehicle. Before that, source the required setup files from the same terminal. Now open a new terminal for launching RVIS2. So we'll be using RVIS2 to test the sensor output. Let's launch the ego vehicle with the default description file, and let's see the available sensors from the vehicle. These sensors can be seen in the RVIS2 topic list. You can see under hero you can see a set of sensors available. These are the one which is attached to the vehicle right now. And right now I'm opening 3 sensors: RGB, depth, and semantic segmentation. Here there is a problem. You can see that the sensor output are with a different resolution. This will not be useful for our project. So we need to have our own custom sensors attached to the vehicle. So first let's have a look into the default vehicle description file available under ROS2 bridge repository. Open ROS2 bridge repository. Under that, src CARLA spawn object, and then config folder. Here you can see objects.json file. This is the default object description file used while launching the ego vehicle. Let's create a copy of this object.json file in our CARLA-ROS2 workspace. And this will be our custom vehicle description file. So rename it to car_definition_file.json. In this file, you can see the list of sensors attached to the vehicle. And here we can see the semantic segmentation sensor and the sensor camera depth, or maybe the depth sensor. Now we will create one more entry for semantic segmentation sensor and one more entry for camera depth sensor. For that, copy this complete sensor description and paste it directly under sensor underscore or maybe sensor.camera.rgb sensor in the beginning. Here we need to change the ID of these two sensors, something like _normal. Basically, this is the topic to which the sensor will publish its sensor output, or maybe the images. Also, we need to make the resolution of semantic segmentation and depth sensor similar to camera.rgb sensor. So let's do that. Here FOV is already same for these three sensors, so they need not be changed. And the spawn point is also same, so we don't have to make any changes there. Only image size X and Y need to be changed. There are other parameters in the same description file. Maybe you can have a look, but for now, this is sufficient for our project. To launch the Ego vehicle with this custom vehicle description file, use the previous command with additional command line parameter called objects_definition_file equal to the path to this description file, which we kept under CARLA-ROS2 workspace. Now let's open ROS2 and see whether the sensor output is really available or not. For that, just check the topic list and see whether the new sensor topic is visible under the create visualization window. Here you can see that those sensors are not visible. Just try to refresh it once again and check the list. Okay, now the sensors are not appearing here, which means it was supposed to be available under hero topic, which means there is something wrong with our object definition file or the way we call the command. Let's have a look into the command. Okay, got it. Yeah, there is a problem in the, or maybe there is a typo in object definition. Okay, now just try it again. Okay, let's check the topic again. Now you can see depth front normal topic is available, and also the semantic segmentation front normal is available. Just check the image. Okay, depth is available now. Also check the semantic segmentation normal. Okay, so these two sensors are already available. Maybe we can add RGB as well. RGB front and then image. Okay, 3 sensor outputs are coming from the vehicle with the required resolution. So our vehicle is ready, or we prepared the vehicle description file for our collision avoidance system. Next, prepare the software section to monitor the collision. Create another ROS2 node to read sensor data and predict and alert user about possible collisions. To create the new ROS2 node for collision avoidance system, open SRC folder and here open a new terminal and then deactivate conda and source ROS2 setup bash file. Then you can run ROS2 package creation command with package name as collision avoidance system. To add the executables, open this collision avoidance system folder in VS Code, and then we'll create the Python script for our functionality. Here I'm going to add a new file named collision_monitor_control.py. This will be our collision avoidance system executable. Now let's add the basic structure to the collision avoidance system node with the node name as collision_monitor_control. Then add a new subscriber to read the RGB images from RGB camera attached to the Ego vehicle. For that, the topic should be Carla/hero/RGB_front/image and provide callback function name as image_callback_RGB. Then define the callback function to read the image in the message format and convert it into OpenCV image. For that, we need a CV bridge. First, we will need to define that, and then we need to convert the received message into CV image. And just for the visualization, we can just show it with the CV2IM show utility. Next, update the setup.py in the package to pick up the right executable from this package folder. Then build the CARLA-ROS2 workspace, which will build navigation and collision avoidance system packages. After that, to test the node, first of all, you need to run the Ego vehicle with the custom vehicle description file, which we created in the previous step. Now the Ego vehicle is launched. Then run the collision avoidance system node from a different terminal. If the node is working properly, then you will see a separate window with RGB camera image. Yeah, you can see that the RGB camera image is already appearing. So this is from the collision avoidance system node. So basically the image is properly decoded in this particular node. Similarly, create another subscriber for reading the semantic segmentation output, and also define the callback function for it. It's almost similar to RGB camera output. Build the package and test the output. So now we need to have two windows for segmentation and for RGB. Next, prepare a subscriber for depth image. And the callback function is not same as that of RGB and segmentation subscribers. Here the encoding is also different. Instead of BGR8, you need to use pass-through. And also before visualization, you need to normalize the received CV image between 0 and 255. But for processing, you need to use the original image that will have the depth in meters. So only for visualization, you need to normalize it. Now we received all the sensor data in collision avoidance system node. Now let's prepare our collision monitoring system. We also need speed information from the vehicle in order to predict the possible collision. So the collision distance will be varying based on the speed. So to calculate it, we will be subscribing into Carla Hero vehicle status topic in order to extract the vehicle speed. So create a new subscriber and also corresponding callbacks function for retrieving this information. Here I am going to use surround monitor.py script for front collision monitoring. There is a class defined in it called surround monitor. This is the one which we are going to utilize it in our collision avoidance system. Then create instance variable for each sensor data and also create an object of surround monitor class with constructed parameter as speed limit. After that, modify all callback function in order to assign the sensor data to corresponding instance variable. And also you can disable the visualization of each image. Then add a new timer in order to continuously run the surround monitoring system for monitoring possible collisions based on the sensor input. run surround monitoring system under timer callback function. It should be run only if there are valid images from the sensors. Otherwise, there should not be any call to the surround monitoring system because it will end up in an exception. The monitor and alert method of surround monitoring system will return two parameters. One is possible collision. The second one is there any object in the collision zone based on the vehicle speed. Build a package and run the node again to see the output of our surround monitoring system. When you run this node, you can see a new window of collision alert system. In this, you can see a polygon at the bottom side with a green color. That is the region considered as collision zone. The polygon will expand as the vehicle speed increases. And at the top, you can see the status of collision avoidance system. The system returns two parameters. First one is collision warning and second one is collision possibility. Collision warning will be returned when a vehicle or pedestrian intercept this collision region. And collision possibility will be returned when the distance between the object and ego vehicle is less than a threshold limit. And right now the output of surround monitoring module is not used for controlling the vehicle, hence the vehicle is not controlled by the software. Next, use the output of surround monitoring module and implement a controller to control the ego vehicle. Basically, we only need to control the speed of the vehicle. For that, we can use speed command topic. So, add a new publisher in the node to publish decide speed to speed command topic. This will be finally used by the local planner to control the vehicles. And the decide speed is set based on the output of surround monitoring module. The speed will be gradually reduced if collision warning detected, and the speed will be set to 0 if collision possibility detected, or we can say it's an emergency braking. Now let's run all nodes together to see the final output. The execution steps are already explained in my GitHub repository, so just open the repository. The execution steps of collision avoidance system is explained in phase 2 section, and here there is a readme document named phase 2 readme.md file. Just open it in a new tab and we can follow the steps. The steps include starting the CARLA server and ROS2 bridge, and then spawn a vehicle with custom vehicle description file, and then use a route planner to find the best route from starting point to the destination point, and use a controller to control the vehicle, and a collision avoidance system to monitor and avoid frontal collision, and a navigation HMI to select the destination location on the map, and use another CARLA Python API example script to launch another vehicle in the simulator and test the behavior of ego vehicle. First, update your repository under CARLA-ROS2 workspace SRC folder so that you will get the new packages which we added. And then once you have the packages, you need to build all the packages and then source it. The steps are mentioned here. Next, open a new terminal and start CARLA server, and keep the terminal as well as the window open throughout the demo. Once the server is running, then follow step 2 to step 4 to launch ego vehicle with custom description file, and then a route planner to find the route from starting point to destination point, and then the controller node to control the vehicle. Next, run the collision avoidance system node. Once the node is up, you can see a status window showing the collision avoidance system's parameters. Next, run the navigation HMI node, and finally launch AVOIDANCE and add all visualization we did it in phase 1 demo. Then select a goalpost and see whether the vehicle is following the route or not. So basically ensure that phase 1 demo is working here also. Also, you can see the status of collision avoidance system in this window. To test the collision avoidance system, we need another vehicle in the simulator, which we will use it as an obstacle in ego vehicle's path. For that, use Carla Python example script to launch a vehicle. After launching the test vehicle, choose a goalpost for ego vehicle in AVOIDANCE map in such a way that the test vehicle become an obstacle in ego vehicle's path. And then see how the ego vehicle handles such situation. Now you can see that the collision detection system identified the test vehicle and applied braking to avoid a collision. Let's test it once again. Drive the test vehicle into a different location and again choose a goalpost for the ego vehicle in such a way that the test vehicle is on ego vehicle's path. Here you can see the ego vehicle is clearly identifying the obstacle in its path and applying the brake in order to avoid a possible collision. Now let's play with our test vehicle. We will drive the test vehicle and dynamically we will create the obstacle for the ego vehicle and see how the ego vehicle reacts to such situation. Here the ego vehicle is driving autonomously and the test vehicle is driven by me. And that's the reason why the test vehicle is moving very aggressively in the simulator. From the output you can see our collision avoidance system is performing really well. Finally, we will see how we can run all of these nodes together with a single launch file. Before that, close all the terminals which we opened except the Carla server terminal. Open a new terminal and source the required packages and then launch master_launch.py from CARLA-ROS2 workspace. This launch file covers 5 operations. First, launch the ego vehicle with custom description file. Second, start waypoint publisher node. Third, start local planner node. Fourth, start collision avoidance system node. And fifth, start navigation HMI node. After running the launch file, you need to open AVOIDANCE from a new terminal and also start test vehicle from another terminal. Then you can continue the testing as like we did it before. Finally, let's have a look into our RQT graph to understand the nodes involved in this project and their communication and the messages involved. Here you can see that all the nodes which we developed are kept under self-drive stack group. With this, we are completing phase 2 demo, but you can try modifying the collision monitoring system node according to your need. Also think of using LiDAR and radar sensors for this task.
Thanks for watching and stay tuned for the next episode with a new problem. Thank you.